to the assistant. Now, the question, let me repeat, is asking you to find the Fourier series coefficients of the output of this system. Sorry, when the input is x of n, which is like this. And the period of this one is 4, by the way. We will collect later, don't worry about that. The period is 4. Now, let me remind, or let me start by reminding with one important property of passing through linear and time invariant systems. And if I'm giving you the impulse response or the frequency response, we will see, automatically that makes the system linear and time invariant by definition. So when a system, when a periodic signal passes through an LTI system, the period doesn't change, the fundamental period. So the output is automatically just another periodic signal with period is equal to 4. That's what we would expect. This simple system with two-tap impulse response is just for the illustration of that. But even for more complicated systems, when they are linear and time invariant, we expect a similar behavior of having an output with period 4. Now, this system is a simple one in it, and it is applying a first difference. Right? You may remember that. When the input is delta n, the output is delta n minus delta n minus 1. And such a thing, such a system, when you convolve with, so xn convolution hn is xn convolution delta n minus delta n minus 1 is equal to nothing but xn minus xn minus 1. So that is yn. The input-output relation could also be given to you like this. It's the same as saying hn is equal to this one, or yn in terms of xn is given like this. That's an input-output formulation. This is an impulse response formulation. And when you apply it to your xn, what will you get? Let's start from a point like this, for example. The difference between xn when n is equal to minus 1 and xn minus 1 is 1 minus 0. So at minus 1, it is a 1. At minus 1, I'm drawing yn. That's a 1. Now what is it at 0? At 0, it is this value minus the previous value. And what is that? 0. It's the same. At 0. At 1, this value minus the other one is still 0. At 2, 0 minus 1 is minus 1. So this is a 1, the other one is a minus 1. And at 3, so this is at 2. At 3, again it becomes 1. And then 2 more zeros. And then minus 1. And then a 1. And 2 more zeros. And then minus 1. And 1, etc. It goes on like this over the axis of n. At minus 2, by the way, it was minus 1 and then 2 zeros. At minus 3 and minus 4, and then a plus 1 and minus 1, 2 zeros. It goes on like this. So as you see, this is another form of a periodic signal, and the period is still 4, because this first appearance of this 0 value appears here, or the distance between this peak and this peak, or this peak and this peak, etc. They are all 4. So we conclude that the period is 4. This is an expected behavior, as I say. It happens to any kind of a linear and time invariant system applied on a periodic signal. The period doesn't change. So this is a new set of sample values for a periodic signal, that is y of n, and the rest is nothing but the application of the formula. You don't really need to tell me exactly how it may be simplified. It may be simplified, but I don't care about that. So the Fourier series coefficients of AK, as we know, are equal to 1 over n, which is 1 over 4 for our case, and the summation, you must decide on a summation interval. It may be a good idea to start from 0 and go up to 3. And then we have x of n e to the minus jk. 2 pi over 4 is pi over 2 n. And by the way, that is necessarily equal to 1 over 4, the summation. The summation from 0 to 3 has 0 sample values for x of n, so the summation running index is unnecessary at n is equal to 0 and at n is equal to 1, because the values are already zeros. Let me forget about the summation. We have only 2 sample values, and the 2 sample values are at n is equal to 2 and n is equal to 3. At n is equal to 2, xn is equal to minus 1. So it is a minus 1 times e to the minus j k pi over 2, and n is equal to 2. Those 2's will probably cancel. Plus 1, because at 3 the value is 1, xn value is 1, times e to the minus jk pi over 2 times n is equal to this time 3. So it's a combination of 2 complex exponentials only for every k. Now, do you remember that the Fourier series coefficient values, AKs, must have only a finite number of distinct values? And how many distinct values do we expect here? We expect 4 distinct values. After 4 values of k, for instance, k is equal to 0, 1, 2, and 3, and then when k is equal to 4, for example, a4 is equal to a0. It must go on like this. Now, I'm giving you, or I'm showing you one very important property of discrete time Fourier series expression for AK. AKs are always in the form of a periodic waveform at the right-hand side, because they are periodic. So the right-hand side expressions are expected to be like complex exponentials, which are naturally periodic, or sinusoids, sines and cosines. There may be some phases if you wish, but other than that, that is the situation. So if you come up with, when I ask a question, if you come up with an AK expression which is weird, which is not very periodic looking, I don't know, maybe k plus 1 to the power something. So as k increases, k plus 1 is increasing to the power of something, is increasing even further. Or it may be a decreasing coefficient, but whatever it is, if it is not periodic, if you're not convinced that it contains complex exponentials or sinusoids or anything like that, then you must be suspicious. There is something wrong. Probably what you did would be wrong. So please check this. And also please check that the whole expression, overall expression, is periodic with 4 in the period index. For example, k is multiplying some integer, here in this case it is 2, times pi over 2, which is 2 pi over 4. That automatically makes the denominator of 2 pi, automatically gives you the period here. In fact, if you cancel with 2, it becomes periodic with 2 pi over 2. So it is periodic with 2. This portion is periodic with 2. Okay. However, this part, the other one, is periodic with 4. So the overall thing is periodic with 4. Well, let's be honest about that. If what you find is periodic with 2, then it is also periodic with 4, and it doesn't violate anything. It's still okay. So anything which is periodic with an integer divided version of your original n. For example, if it is periodic with n over 2, then it's also okay. If it's periodic with n over 3, it's also okay. It's still okay, because it automatically makes everything with periodic with n. So please check this. The Fourier series coefficients must be periodic with your period of the signal. And that is usually satisfied by complex exponentials or sinusoids, as I say. Now, I wasn't doing or asking this kind of a question in continuous cases, but in continuous cases, if you remember, I was usually giving you the so-called frequency response, right? A filter shape, a triangular shape for the quiz question yesterday, for example. That is still possible here, but what is the formula to obtain it, or what kind of properties does it have? And it will be called, by the way, e to the j omega, h of e to the j omega. Do you remember what we were calling for the frequency response in continuous time? How were we indicating? If you remember the quiz question yesterday, first hour, I called it h of omega. Remember that? Because it's a function of omega. Now this is also a function of omega. E and j are just numbers. The parameter here is still the frequency omega. But why am I indicating it in the form of e to the j omega then? H of e to the j omega. That comes from this fact. E to the j omega is naturally periodic with 2 pi. And what we really indicate or emphasize by this notation is that this thing, the frequency response in discrete time systems, is always in that form. It has e to the j omega formalism. And it is naturally 2 pi periodic. For instance, it may be something like this, around 0. This is the cutoff frequency, omega c, and this is the minus of it. This looks like a low-pass filter, some sort. It's not passing high frequencies, but it is repeating itself at 2 pi and even further than that. 4 pi, 6 pi. And in the negative axis as well. So this is the shape that you expect for h of e to the j omega, the frequency response of discrete time systems. And it has a relation with h of n. Of course, it can be derived from h of n. This was the frequency response of continuous time systems. So there is a difference in notation, even in the frequency response case. So how are we going to find the outputs when things pass from such filters? I'll look for a colored chalk if we have any. Yeah. Now I'm going to draw the Fourier series coefficients with this blue chalk, and they will be placed on this so-called spectrum. If the axis is a frequency axis, what you are looking at is called the spectrum. So in the spectrum you have Fourier series coefficients. Let's assume n is equal to 8. Okay. If the period is equal to 8, it means you have 8 Fourier series coefficients, distinct Fourier series coefficients. And where are they located? They are located here. This is A0, some value, at frequency 0. And at frequency 2 pi, it repeats itself. So n is equal to 8 coincides with this. This is A0. This is A8, which is the same as A0. And then this is the point of pi. This is pi over 2. This is 3 pi over 2 points. The other Fourier series coefficients are at the intervals of 2 pi over 8. So intervals at 2 pi over 8. Where are they? For example, one of them is at 2 pi over 8 is pi over 4, so it is somewhere here. This one, for example, is A1. Guess what? At the same position, starting from 2 pi, you have A9, which is the same as A1. At the point of pi over 2, you have A2. And here you have A10, which is the same as A2. Here you have, let's assume, some negative values. They are in fact complex values, but I'm unable to draw them that way. A3, A3, and it goes on like this. At pi, some value A4, then A5, this is A6, let's assume, and we have an A8, sorry, A7 of course, and then you come back to A8. This is just an imaginary layout of Fourier series coefficients, of course. Honestly speaking, I would expect, for example, A7, this one, which is symmetric around A8, or that A7 is, by the way, equal to A minus 1. So let's also draw something here, which is the same as A7. That is A minus 1 here. So A minus 1 is the same as A7. A0 is the same as A8, etc. But of course, around 0, the magnitudes of these things are expected to be the same if it's a real signal, by the way, but I didn't draw it that way. So for a real signal, we expect the Fourier series coefficients of A minus 1 and A1 to be conjugate symmetric, and conjugate symmetric values are having the same magnitudes. So now your Fourier series coefficients must be overlaid on the spectrum like this. If it is 8, it is like this. If it is 9, you must divide between 0 and 2 pi. You must insert 9 coefficients then. If it is 10, you must insert 10 coefficients, etc. And the intervals, therefore, are changing by the value of your period. And this is just an example of 8. Then what happens when you filter your x with this filter of h, whose spectrum is drawn with these white figures? Every value of ak, for example, this one has Fourier series coefficients ak's, and this one will have bk's equals ak times the spectrum or the frequency response of h at that corresponding frequency, h of e to the j omega, At the corresponding frequency, what is that corresponding frequency? At frequency k times 2 pi over n, evaluated at k times 2 pi over n. For example, if k is 0, then b0 is equal to a0 times h of e to the j omega at omega is equal to 0. What is that? This value, for example, whatever that value is, it is multiplying this a1 level. Similarly, this value here, which is the value of h of e to the j omega at omega is equal to 2 pi over 8. 1 times 2 pi over 8, in other words. That value is multiplying a1. And you will get b1. b1 is equal to a1 times h at omega is equal to 2 pi over 8. Here, b2 is equal to a2 times h of omega, h of e to the j omega, evaluated at omega is equal to pi over 2. What is that value for this example? What is this value? It's 0. So a2 will not pass. a3 will not pass. a4 will not pass. a5 will not pass. a6 will not pass. a7 will be multiplied by this value. a8 will be multiplied by the same value of a0. And it goes on like this. So in effect, this system, if this is your system of triangular spectral shapes of h of e to the j omega, then it is passing only a minus 1, a0 and a1, and its 2 pi periodic replicas, which means it is passing only the low frequencies, because pi over 8, 0 and minus pi over 8 are low frequencies with smaller frequency value, and the high frequencies are the frequencies around pi, as I said yesterday. Around pi, these are high frequencies and they don't pass. They are all those harmonics are annihilated, suppressed by multiplying with 0. And they don't pass. They don't pass here, they don't pass here. All the 2 pi periodic replicas, they are all annihilated similarly, suppressed, and only the lower frequencies are passing. So we call this shape some sort of a low-pass behaving shape. But whatever the shape, regardless from the shape, this is what you're supposed to do. I will give you an H, a system, and I will give you an input. From that input, you need to evaluate the Fourier series coefficients first. From those Fourier series coefficients, you will multiply each Fourier series coefficient with the h of e to the j omega function at the corresponding frequencies, of course. For example, here again, it's minus pi over 4, pi over 0, pi over 4, pi over 2, etc. And you will get an output, BKs, a suite of BKs. How can you further proceed with the question? I may ask you, for example, what is the signal at the output? Then from these new Fourier series coefficients, you must combine with the harmonics and say that y of n is equal to that summation. And remember the summation formula, or even if you don't remember the summation formula, it will be available to you. It's just the Fourier series representation of discrete time signals using the Fourier series coefficients from the harmonics. Now, as a homework, which I will not collect, okay, this will not be collected, but it may be asked in the exams, and the questions are, or the questions will be similar, of course, in a sense. Go back to the same quiz question, and first you need to derive h of e to the j omega. By the way, sorry about that, I didn't show you what h of e to the j omega is. Let me first derive the formulation of h of e to the j omega, and then from there I will ask the homework question. So the formulation is as follows. What is the relation between hn and h of e to the j omega? So how can we evaluate that? That or such things are usually obtained by passing a pure sinusoid, which is e to the j omega n. This is a pure sinusoid with frequency omega. Let's call it omega 0, a specific frequency. So this is a pure sinusoid. If this pure sinusoid goes into a system H, what is the output? For that you need to convolve, of course, e to the j omega n by h of n. And in this convolution, you will have a large summation formula here times e to the j omega n. That will come from the convolution. We did it already in continuous time. In discrete time, let's not do it, but instead let's give what that formulation will give you. It will give you the formula of h, which is summation k from minus infinity to infinity h. Let's not okay, let's do it in terms of k. H of k e to the minus j omega k. In this convolution, you remember that you say inside the summation h n minus k multiplied by h of k minus n multiplied by e to the j omega k, or you may convolve in the other way around and say hk times e to the j omega k minus n and make a summation. That minus n will eventually go out, and this summation will only be in terms of k, like this. When you do the convolution, this is what you will get. But that thing, as you see, doesn't depend on n. There is no n term appearing over there. It is only in terms of what? K? Is it in terms of k? It's not even in terms of k, because k is in the summation index. So k doesn't come out of this summation. It is only in terms of omega, nothing else. This summation is nothing in terms not in terms of k. It's not in terms of n. It's only in terms of omega, and we are going to call it h of omega, or to be more specific, h of e to the j omega. So that is the function that we're looking for. What it is saying is, when e to the j omega n, omega 0, and this is also in terms of omega 0, by the way, everything has omega 0 here. When e to the j omega 0 n goes into an h, the output is h of e to the j omega 0 times e to the j omega 0 n. This is the same formalism that we had in continuous time. If the input is a pure sinusoid, the output is the same pure sinusoid scaled by a function of frequency. Just like that one. And notice that in harmonic representation of Fourier series, every such signal is multiplied by some coefficient, a, and it is summed up. So since this is linear, this a is multiplied at the left hand side, and it is summed up again. So if this signal is x, the input, this signal is y at the output, with the new Fourier series coefficients given as the old Fourier series coefficients multiplied by the frequency response. So the formula for the frequency response comes from this fact, and let's write it down here and put it inside the box and leave it as the formula to obtain h of e to the j omega, this function, for example, these white triangles, from h of n, which is the impulse response. That is the relation. So h of e to the j omega is summation k from minus infinity to infinity h k e to the minus j omega k. I skipped a lot of details here. I didn't derive, for example, why this is the true formula. But it comes from the convolution, and you can do it at least. I don't say you can easily do it, but you can do it. But the formula here is, for the time being, more critical to us, and we will use the same formula over and over again in all sorts of discrete time systems. We had a similar formula in continuous time. Do you remember that? Do you remember the relation of h of omega in terms of the continuous time impulse response? Instead of the summation, there was an integral, and it was x of t e to the minus j omega t dt. So this was the relation from minus infinity to infinity, of course. This was the relation to convert our, it's not x, I'm very sorry about that, it's h of t, the impulse response of h of t to the frequency response, and this is the relation of impulse response to frequency response in discrete time. These two things, these two formulas are the ones that we will commonly use. We will start using them next week, in fact, once we are finished with this topic. Now let me ask you the question, because you have the formula now, this formula. Use this formula to find let's erase this part. And it will be a good exercise for you as a homework. H of n was equal to delta n minus delta n minus 1. So part A of the question, what is this? Just apply it to the formula and find it, and answer these questions. Is it 2 pi periodic? It must be. If it's not 2 pi periodic, then it means you didn't use the formula good enough. It must be 2 pi periodic. Part B, plot, find and plot. Find and plot the Fourier series coefficients of x of n on the omega axis. So what am I asking you here? I'm asking you to plot the Fourier series coefficient of x of n like we did for these blue Fourier series coefficients. And A0 will have to repeat itself one period afterwards at 2 pi. What was the period here in this question? It was 4. So A0 is here, A4 is here, and A3 is here, A2 is here, A1 is here, by the way. I'm showing you the places already. You will find 4 distinct Fourier series coefficients, and you will insert them like this: A0 here, A1 here, A2, A3, and A4 will be the same as A0 at exactly 2 pi. I want you to do it. I want you to find the Fourier series coefficients first. First you have to use the formula to find the Fourier series coefficients and put them, render them on the frequency axis, on the omega axis. Okay? Evaluate AK times h of e to the j omega at the corresponding frequency, because AK is at a specific frequency of omega 0 times k, which is 2 pi, or let's call it like this, omega is equal to 2 pi over 4, n is 4, times k. For example, A0 will be multiplied by h of e to the j omega at omega is equal to 2 pi over 4 times 0, at omega is equal to 0 in other words. So just multiply everything and call them BKs. 4 of them is enough because they are repeating themselves afterwards. So find B0, B1, B2 and B3 only, and the others will be repeating. And finally, as a part D, verify our previous answer that I have erased from here. We found that it contains only 2 harmonics. Probably something is happening in such a way that 2 of the harmonics are either multiplied by h of e to the j omega, which makes zeros. Probably these become zeros at 2 points, so that 4 of the Fourier series coefficients will not, 2 of the Fourier series coefficients will not pass. 2 of them will shrink down to 0, and we will only have 2 Fourier series coefficients. You remember that in the expression that I have erased, there were 2 complex exponential terms. One thing, e to the j something plus e to the j something else. Either that way, either this is causing it, the system is causing it, maybe, I don't know, or originally these AKs were already zeros. Then no matter what a filter may be, if this is 0, 0 times something will give you a Fourier series coefficient of 0. That is also possible. I don't know which. Okay? Just work on it and verify that our previous answer are the Fourier series coefficients, the 2 Fourier series coefficients that can be found this way as well. This is quite an indirect way of finding the same solution, but in some other cases where h of n is not as simple as this one, if it is too complicated, then convolution of this thing with h will be a bit more difficult. In that sense, there are cases where evaluation of h of e to the j omega from that complicated impulse response could be easier, and this will give you a very nice and easy shape sometimes. So it will be easier for you to multiply this shape here with the Fourier series coefficients and evaluate your new set of Fourier series coefficients, and then combine them to get the answer. Okay? Is this clear? Filtering on the frequency axis is something very critical. Okay? You must understand it very well. And Fourier series coefficients is a representation on the frequency axis, the blue curve, the blue plots. The other one is the representation of the system. And what you really need to do is you have to just multiply them. And filtering is usually like that. It's a multiplication on the frequency axis, on the spectrum axis. And we will again and again come up with this conclusion. In Fourier series, it was in Fourier series already, both in continuous time and in discrete time. In the next week, we can stop now, in the next week, we will start the non-periodic version of it, which is called the Fourier transform, and the same spectral domain multiplication for filtering will be valid. Okay? So we can stop now.